Thanks, Asfa, for the introduction there. By the way, I did a quick check, and actually, Jenna's presentation on human-in-the-loop anomaly detection is actually today at 1. So
yes.
If anybody here is psyched about machine learning after watching this presentation, stick around for that one. It's probably more or less that. So I'd like to start this out by giving you guys an outline of the presentation you're about to look at, because there's a few things you may want to know about. First and foremost, I recognize that many of you are not machine learning experts. And in order to talk about some machine learning topics, I'm going to have to give a brief overview of several of the basic concepts within machine learning. So that's the first thing I'm going to be doing here. Then I'm going to be giving you guys some information about issues within machine learning when we try to apply it to cybersecurity problems, specifically related to data, although it's not going to be just the things you might have heard in my poster presentation last week. After that, I'm going to be focusing on what the cybersecurity applications we're using for applying machine learning to, which are mainly intrusion detection, incident response, and automated red teaming. And something I'd like to note beforehand here is that not all of this is tools that we're going to see very often in industry. A lot of this comes from current machine learning research, but I would like to see that some of these applications be ported over to industry so we can actually see these being used in practice, because I think some of them can actually be very helpful. And then finally, I'm going to go over whether I believe that machine learning is worth it for cybersecurity, and I'd like to solicit some response from you guys as well on this topic. So, first things first, what is machine learning? I believe the best way to define this is a little informally, which is I consider machine learning to be a collection of techniques that enable a machine to learn the definition of a function. So thinking of a mathematical function here, we have a mapping from one set to another. We call the first set the input set, and inputs for machine learning tasks typically tend to be what's called feature vectors. So you can imagine this as some fixed size array of values that are probably going to be like real number values. If you're into systems programming, it's IEEE 754 floating points, most likely. And to give a good example of that, I'm going to turn to a common machine learning task, which is digitizing text, right? So say we have some old newspapers or books or whatnot, and we put them into a scanner, and we have a bunch of images of each of the letters or numbers or whatnot, but we don't know like how we should transform that into our ASCII text or whatnot, right? Here we've got some examples of handwritten numbers, I believe from the MNIST dataset, right? And the way to think about this particular task is like, okay, first, what is the feature vector going to look like, right? And here we have, in each case, a fixed size image. That's actually very important. So we could say these are like 30 by 30 pixels, right? So we could take that and turn that into 900 size feature vector, right? Where each pixel, right, is some value that will say 0 maps to the black pixel and 1 maps to the white pixel, and all of the grays in between are somewhere in the middle of that. And so we'd be learning a function that takes 900 values between 0 and 1, and it's going to output some number or letter or whatnot. And that's kind of what machine learning is trying to do. And we divide machine learning into three main approaches that I'm going to be covering in these coming slides, which are supervised machine learning, unsupervised machine learning, and reinforcement learning. The first of these, I think, is probably one of the best research because there's so many algorithms for it. That's supervised machine learning. And the task that I had just talked about, which was classifying the MNIST handwritten numbers into actual numbers, is an example of supervised machine learning. So we have a data set that has all of our inputs and all of the outputs for that. Great. Now all we have to do is find some function that's going to correctly predict all of the right outputs for all of the right inputs. But one small caveat, we probably shouldn't try and train that function on all of the data we've got. Because if we do, we have no ability to test it on other data. And that's kind of what we want machine learning to do, is we want a function that we can use to predict things. So what we'll do with our supervised machine learning is we're going to divide our data set into two parts. One we'll call the training data set, and one we'll call the testing data set. There's also sometimes dividing it into three sets. We'll have one we'll call the validation data set that's used in training. But you will take whatever machine learning algorithm you've got and train it on that training data set, and you will evaluate it by having it predict a testing data set that it's never seen before. And if it gets good accuracy on that testing data set, then you know you've got a good model. Now, tasks in supervised machine learning generally tend to be one of two things. First is classification. So our output for a classification task is going to be a class label. We're trying to find out what group something is. So an example of this type of task might be classifying road signs. Say you've got a self-driving car, it's looking at pictures as it's driving along the roadway, right? It's saying, is that a car? Is that a stop sign? Is that a yield sign or something like that? And the other type of task is a regression task. And here our output is a real numbered value. So for instance, 3.3598 for that note. And as an example of a supervised machine learning algorithm, I'll provide you guys with neural networks. So if you guys come out with nothing from this, at least you'll know how a neural network works. So the idea here is that we have several layers of nodes, and each of those layers is going to have a weight and an activation function. The first layer is for taking an input from the data set, and that should have as many nodes as we have values in our feature vector, right? Then we have one or more layers that we'll call hidden layers. These are the middle layers, and what they do is they will take values from the previous layer, and they will multiply it by some weight, and they will then apply an activation function, transforming all of the values they've received there, right? And the weights in these hidden layers is what we're trying to train. So as we get mispredictions, we're going to propagate back towards those weights and use some sort of correction to change those until eventually the weights stop changing. Finally, we have our output layer, which we might actually want more than one of. And that is going to use an activation function to produce the output. And some of you might not understand what that activation function idea is. So one way to think about this is, how do we do classification? Because everything I've talked about thus far is basically just doing mathematics, right? We are producing real values at every step. So how does that turn into label, right? And so one example of an activation function is the sigmoid function, which is going to take whatever its input is and output a value between 0 and 1, right? So if we were doing something like binary classification, that is where we're only having two labels, we could say, okay, if this value is less than 0.5, we're going to use the first class label. And if it's greater than or equal to 0.5, then we're going to use our second class label. And we can further say, okay, what if we want to do multi-class classification, where we've got 3 or more classes? Well, then we could have one output node for every class. And in each case, we're going to output a value between 0 and 1. And then we're going to want to pick the value that produced the highest number. So you could say that the value between 0 and 1 is our confidence that this is the right class, right? So we're picking the right one there. And so that's kind of how you would use a neural network to do classification, right? But then we have the case where our data set doesn't have any labels. And that can make things a little bit of a problem because, if you want to figure out what group something is part of, it helps to know what group other things like it are part of. But that's not actually too much of a problem if we're willing to make certain kinds of assumptions, right? So unsupervised learning is going to be, instead of trying to find a perfect mapping based on the training data, it's going to try and find some sort of pattern within the data set. And when we do this, we're going to want to make a few assumptions to be able to make use of this correctly. So for instance, we need to at least know how many classes there are if we want to do some sort of classification task. I'll also note that there is, on a related subject, semi-supervised learning that I haven't created a separate slide for, but it has some similarities to unsupervised learning. And basically, the idea is that some of the values will have labels, but not all of them. And so you can use the ones that do have labels to sort of guide correctness here. And as an example of an unsupervised machine learning algorithm, I'm going to provide you guys with the K-means clustering algorithm. So in this diagram here in the top left corner, you're going to see that we have, let's see here, 12 different gray values, right? We don't know what class those are, but we're going to say there's 3 classes, right? We're going to start by randomly creating points in this data plane, which we'll call centroids, right? And I've kind of made a little bit of a typo here. We're not moving values to our centroids, but instead, we're going to iteratively first say that every value is the class associated with its closest centroid, right? And then we're going to move the centroid towards the center of all the values in that class. And then we're going to repeat this process until we no longer have a change in the classes for each of these things. So in our final vector, right, you'll note that we'd move the centroid from having one red block here over towards its one red block since that's the center. And then now, to those green blocks, we're closer to it than to the other centroid, so they just changed classes, right? And once it stops changing classes, that's when you can say, okay, we found these 3 classes, and these are the values we think they are associated with. So that's unsupervised learning. And finally, we're going to talk about reinforcement learning. And for this, we were talking mainly about like how do we classify things. And now we'd like to talk about how do we act. We'd like a machine learning model to act. We've got some sort of environment for an intelligent agent to act in. And we'd like to find what we'll call a policy that's going to define how that agent should act. And that policy is our function that we're learning, right? It's going to say, if we have these scenarios going on, this is the best action you should take at this time, right? And all of these actions do have the ability to change the environment we're in. So this is a bit different than dealing with some static feature vectors that we're used to, right? Additionally, those actions will generally offer a reward from whatever model the environment is having. And our learning model is based on how do we maximize that reward. So as an example of reinforcement learning, I will offer to you the Q learning method. And this does not actually use a model of the environment. So you don't need to program in what the environment is from the point of view of the AI here. Instead, we're going to start by having some table of states and actions, right? Which we will call Q. This is our Q function, right? So our columns here are actions, and our states are our rows. And our example here, we've got some sort of agent that can move throughout a grid, I'm guessing. We've got like the ability to move south, north, east, west, and the ability to pick up or drop an object. And all the values in this table will initially be 0. And the reason they're 0 is to say that we don't know what the reward is, so that every action should initially be equally worth it, right? So our agent, while it's training, is going to randomly select between 2 options. One is to explore the environment, which is to take a completely random action for its state, right? And then figure out what was the reward received for taking that action. And it's going to record that in its Q table. And the other action is going to be to exploit, which is to say, okay, we've got some values in our Q table. Let's take the action that has the greatest reward. And if we were to just exploit once we've, say, filled out a couple of actions, then we might not be able to learn certain types of properties about the environment. For instance, say you're going through a door to get a reward, and 9 times out of 10, it offers you a reward of 0. But 10% of the time, it offers you a reward of 100. So ideally, you'd like to go through that door many times to, in the long run, get a higher reward than a door that, say, gives you 1 every time. So you need to be able to explore, and that's one of the things Q-learning will allow you to be dealing with. And once you've finished your training, you have a nice table that you can say, okay, just follow this table and take the best action every time in terms of what we expect the reward to be. So now that you guys have learned a little bit about machine learning, I have some questions for you. First, what are some challenges you think that might come about trying to use machine learning for cybersecurity problems?
You talked about unsupervised learning. It's pretty interesting. I know that there is a project. It's kind of like over time, over training iterations. If you do it too much, it almost turns into a Pavlov's bastard. So what happens is you'll teach a machine learning program to play Tetris, and you'll give it the objective to run the game for the longest amount of time, right? And then you'll start it. It'll start doing its thing, and you'll just hit pause. So what I'm thinking is if it were possible to relate it to cybersecurity.
Oh, I think I remember that. That was a reinforcement learning program that learned to just hit pause because it learned, hey, if I do that, I don't lose any more rewards.
Exactly. Yeah, you can't lose if you're not playing the game. So, curiously enough, if that were ported to a security application, I feel like over training iterations, it would figure out. And this is one of the axioms that my mentors tried to burn into me. Any computer can be hacked. So I think with that axiomatic presupposition, it would just turn off the computer.
Okay, that's fair enough. Any other ideas here? Oh. All right. Second question. Could there be security concerns for machine learning problems even when machine learning is not used for a cybersecurity application? Okay, yeah.
So when you train a model, it just generally sits there in a file, and you don't touch that file after training, right? That's usually how that goes.
Yeah.
So if that algorithm were to be reverse engineered and then modified to give an unexpected result at an opportune time, that would have ramifications.
Someone were to modify the model?
Yeah.
All right. That's fair enough. Any other concerns people might have? Go. Software supply chain attacks. That might be one way to consider a threat on a machine learning application. Say, if we were to take PyTorch and add in some corrupt code somewhere by, say the maintainer of PyTorch were to get really pissed off one day. I can see that happening. All right. Any other thoughts?
Are there any questions about accuracy? Because you might have a really good model and it takes one mistake.
Yes. And I'm actually going to talk about that a little bit later. Any other concerns? No? All right. Some good answers here. So, one of the concerns I have for machine learning applications in cybersecurity is related to data. So, when we're talking about the supervised learning approaches, right? We needed data that was labeled, and preferably a decent amount. The problem is, in cybersecurity, as there is in a few other fields, there's not a lot of good data. And in particular, part of the reason for that is that labeling data takes time. It generally requires a human to do that job. And if we consider how much value is an expert in cybersecurity, then say we have 500,000 NetFlow records, and we'd like you to write down on a check mark or something like that which ones you think are malware. How many people would want to do that for a living? Not a single one of you, and you're all going to be cyber experts. The other thing is that simulating attacks also takes time, and if you want to have a data set that contains both examples of cyber attacks and examples of regular machine activities, you need to be able to carry out some sort of simulation. Alternatively, you need to be able to get that data from someone who has already been attacked. Now, imagine you're the head of SEL and you've just experienced a cyber attack, and someone comes up to you and says, hey, could you give us the logs from the last 3 months of your computer network so that we can use that for machine learning? training? What's the chance this guy's going to say, sure? I mean, maybe if he's really generous, he'll anonymize it and then give you that. And maybe that anonymized data might not be as good as non-anonymized data. And maybe anonymizing it might take a little bit of extra time that, yeah, that's going to cause problems. And then organizations are going to be able to say, flat no. If your hospital got hacked, and we've had hospitals get attacked through ransomware and such, you're not going to be legally permitted to share any of that data for any reason, especially not with cyber experts. So that's kind of a problem. But here and there we do get some data sets getting created, right? And then the problem is that those data sets can get outdated. So here at the left, I've got a table of the various attack types in a data set called KDD99. And this data set is rather balanced, I'd say. We've got a decent proportion of this is normal traffic, and we've got a decent number of various different types of attacks, right? Can anyone spot the problem here? Come on, I know someone's got this. All right.
Do we have like a tiny amount of the user to root attack types compared to the other ones?
That is kind of what I expected someone to answer, but no, the actual problem is this is KDD99. This is a data set created by DARPA in 1999. And this data set was used for some 10 to 15 years after its creation. And so if you're trying to train a machine learning model that hopefully is going to be able to, or even evaluate a machine learning model, right? It's hopefully going to be able to find attacks in this modern day and age. Is this data set good? No, it's old. It's using attacks that were very common for 1999, but not necessarily for 2022. And while I'd love it if DARPA were to, repeat what they've done here every 2 to 4 years, I don't necessarily think that even they've got the funding to be doing this regularly, because this required a lot of cyber experts to create a lot of simulated attacks that they could use to evaluate the intrusion detection systems at the time. Also, on top of data being very difficult to obtain, we don't always know if the data we have is relevant. And this is a case that I've been working on a little bit in the past with my tomato project, and currently with a couple of my undergrads. So what we're going to be trying to find out here is how do we measure that relevance, which I call observability, right? Some more issues on data, all right? So I've mentioned before that a lot of machine learning algorithms like to work with feature vectors that have real value things, right? But most types of things you'll work with in cybersecurity data is very categorical, and it might actually be some value that's like an integer, but that's not really going to be mapping as well to floating point values, right? Let's say we have ports, right? It's a value between, I think, 0 and 65,536. Let's say I decide to just take that and turn it into whatever the floating point number is. So what's an off by 1 mean here? Because ports say 21 and 22 or 22 and 23, right? I think that's Telnet, FTP, and SSH somewhere in there. Not positive. But they're not quite the same application. And in fact, an off by one error here is quite a bit of a problem, especially if we're doing, say, generative machine learning, which I've been working on with my SuperGAN project that is trying to generate NetFlow data. But we do have some ways of representing categorical data, right? The first is called one-hot vector. So if we look at this table at the left, right? We see we have three classes, right? A one-hot vector is to say, for every class, we're going to have one feature. And we're going to say that feature is equivalent to is a member of this class, right? So it's one if it's a member of that class, and every other one of those features is zero. And if you have not a lot of classes, this is actually a great way to represent categorical data. If you have, say, all of the ports in the port range in your data set, you might not want to create 65,536 floating point numbers. That's a bit excessive. And it's going to take a lot of memory to store that. And the alternative way to do this, there's actually a few others, but these are the main ones I see, is binary encoding. So this might be a great way to encode certain types of integer data. And we know if we're trying to represent a number in binary, right? We say the first number is 2 to the 0, and the second number is 2 to the 1, etc., right? And so we know ports are 16 bits. So we could represent a port with 16 different floating point numbers. That's pretty dang great. And in fact, I rather like binary encoding as a way of representing categorical data, to the point where I actually used that for IP addresses on the same generative problem. In fact, I even shortened it to 12 bits because I recognized that I had all of my IP addresses within like 11 different /24 blocks. And so I could say 4 bits and make that say what the /24 is, and then 8 bits for what that remaining octet is. So that's ways you could deal with categorical data. And next, we've got some issues related to structure, because all of the approaches I've talked about thus far are assuming that we still have feature vectors. And what we'd like to have in most machine learning algorithms is a vector of vectors, matrix, right? So we've got, say, 900,000 different vectors. Each one is independent of the other, and each of those, say, might have 50 features. And so we've got a matrix that's 50 by 900,000. It's very nice. We can just apply matrix multiplication to get certain types of algorithms. It's great. So what if the data we're dealing with is not able to be structured like that? The first type of thing I'm looking at here is, say, graphical data, right? Did anybody have a chance to see Nathan's poster? Yeah. So that was dealing with function call graphs, right? And right here, we've got a small example. So we start at our main function, and that's telling you every function that's called from main in order. And then we've got some function that's in turn going to call a bunch of other functions, right? Can we transform that easily into a feature vector? Not necessarily. I mean, this type of thing could be of any arbitrary size. That's kind of a problem if we want to turn it into a fixed size vector. There's probably some algorithms you could use, but you might want to use something dedicated to dealing with graphs. And then we have time series data, right? So I talked about net flows earlier. Say we're talking about simple packet captures, right? We might talk about one transaction going on our network that takes 3 packets and another that takes 5 packets, right? And each of those packets might have variable length of data to go on. So that's even more of a problem because we're not dealing with fixed size anything anymore. So we're kind of going to need to be able to deal with time series data because within security data, we can have events that on their own are perfectly benign. But if they're seen together, that's a problem. So for instance, let's say we've got 3 machines on a network. We'll call them A, B, and C. If A connects to B over SSH, that's fine. If B connects to C over SSH, that's also fine. If A connects to C, then that's a problem. But what happens if we see in a very short time frame that A connected to B and B connected to C? Then, that's kind of a problem. And if we are only looking at independent events and not being able to look at things as a time series, then we won't be able to see that kind of a relationship. And so for all these types of problems, there are specialized algorithms within machine learning. Graph neural networks are a great way of dealing with graph structured data. Structured prediction is a sort of generalized approach to machine learning that doesn't really make as much assumptions about the structure of the data you're dealing with. And for those of you who are WSU students and who might be interested in machine learning, I would highly recommend that you take Jan's class on structured prediction the next time he offers it, because it will go into all of these different ways that you can try and approach data that is not necessarily structured nicely. All right, so Ossify has recommended that I offer a 5-minute break somewhere halfway in between the presentation. So if you guys want to go stretch your legs and get a bite to eat, I've got maybe 12 more slides after this.
Does that sound like a good idea, or do you want? Yeah, that sounds like a good idea. 5 minutes break, or we can make it 7.
If you want